Okay, so welcome to a lecture on ions and isotopes. We're looking today at when atoms aren't normal, when they're strange in some way. And we're going to be looking at two variations in atoms that we can have. So ions and isotopes is the title of the lecture. And take a moment and write that down. Okay, so we talked a couple of lectures ago about the fact that in a neutral atom, the number of electrons equals the number of protons, and that's the atomic number of the atom. How many protons an atom has is what determines what kind of atom it is. Hydrogen is hydrogen because it has one proton. Carbon is carbon because it has 6 protons. In a neutral atom, that's also the number of electrons it has, but that isn't always the case. Atoms aren't always electrically neutral. And the number of neutrons that an atom has can change as well. So if something has 6 carbons, if something has 6 protons and 6 neutrons, it's carbon. If something has 6 protons and 5 neutrons, it's still carbon. The number of neutrons, the number of electrons does not determine the kind of atom that it is. The kind of atom that it is determined by the number of protons. So electrons and neutrons can change, and it's still carbon. It's just some variation of carbon, but it still will act like carbon and do the things that carbon does. So when the charges are balanced, there are the same number of protons as the numbers of electrons. And so we would call that a neutral atom or a balanced atom because protons are positive. So if you have 6 positive things, electrons are negative. You have 6 negative things, positive 6 and negative 6 is 0. The atom is neutral. Okay. Protons have mass, electrons do not have mass. And so the number of electrons that an atom has does not affect its mass number. And so you can have more or less electrons and the mass of the atom does not change. Neutrons do have mass and they are in the nucleus, but they do not have charge. So protons have mass and charge. Electrons have charge but no mass. And neutrons have mass but no charge. And so all these particles are slightly different from each other. And the way that they're arranged in an atom controls how the atom behaves and what occurs. Okay, so this again is carbon. So the one I'm kind of using as my example atom here. It has 6 protons in the nucleus. It has 6 neutrons also in the nucleus. And it has 6 electrons in the electron cloud around. This is a simplified model. We've drawn 4 electrons in a ring, but you're smarter than that. You know that in truth that isn't correct. There would be 2 in a sphere, and then 2 in a sphere, and these other 2 would be in that first p orbital, the like Q-tip looking thing, right? But for the sake of simplicity, it's been drawn in the planetary model where they're just all orbiting in rings. So 6 protons, 6 neutrons, 6 electrons. It has 6 protons and 6 neutrons in its nucleus, so it has an atomic mass of 12. And if you were to look at carbon on the periodic table, you would see that its atomic number is 6 because there are 6 protons, and its mass number is 12 because it has 12 things in the nucleus. The number of electrons does not affect the mass. We don't count electrons in mass numbers. Okay. It has 6 protons and 6 electrons, so it has a net charge of 0. This is a neutral, normal carbon atom. Move, slide. Oh, come on, I hate it when it does this. Move. There you go. But things can be different. Okay, so what happens if these ratios change? What happens if we don't have the same number of protons and electrons? Or what happens if the number of neutrons changes? Well, then we still have the element that it was. As long as the proton number didn't change, it's still the same element. But it's an ion or an isotope of that element. So if the number of electrons and the number of protons is not the same, the number of electrons does not equal number of protons, then there's a charge to the atom, and it's called an ion. So if we were to have 6 protons and 10 electrons, then we would have plus 6 minus 10, and the charge would be -4. Okay? Or you could have 6 protons and 2 electrons. That would be plus 6 minus 2, and your charge would be +4. So if you ever have a dissimilar number between protons and electrons, you wind up with an ion. Okay, and how things ionize controls how they bond. Hydrogen can become a positive or a negative ion. Some elements like carbon can also become positive or negative ions, but most elements go one way. Chlorine will only ever be a -1 ion. Potassium will be a positive ion. And I'll show you in the periodic table in just a moment how to predict the possible charges that an ion can occur. But an ionization happens whenever the number of electrons changes and there's not the same number between electrons and protons. So going back to our atom, if I were to show you the same carbon atom, still 6 protons and 6 neutrons, still has a mass of 12, right? But now we've picked up some additional electrons, okay? And so now I have 10 electrons and 6 protons. This is an ion of carbon now, and it's an ion with a -4 charge because it's picked up more electrons. Okay, it's electrically charged now, and we use the term ion. Okay, we're going to write that down for just a second. Okay, so ions are either positive or negative, depending on how the math works out. If they have more electrons than protons, they're negative. If they have more protons than electrons, they're positive. When an ion is formed, we can only mess with the outermost energy shell, the outermost energy level of electrons. And so for elements that are in the S or P blocks of the periodic table, that means that we can only mess with up to 8 electrons, because the S has 2 and maybe that's the outermost one, or the P has 6 and maybe that's the outermost one. So for most of the periodic table, or the elements that we're going to be messing with most in our kind of chemistry, you're going to only see charges that are somewhere, that are going to be, well, less than positive or -4, because it'll either gain 4 or lose 4 to fill up its energy level. The outermost energy level only holds 8 electrons for most of the elements that we are concerned with in this class. And those are valence electrons. The outermost energy level is called the valence electrons. For elements in the transition metals and for the lactonide and actinide series, the ones in the middle part of the table that are justified downwards, then it gets more complicated because the outermost energy level has like 32 electrons or something like that. And you can have tons of different charges there. But for the most part, high school chemistry, we're going to be worrying with S and P elements most of the time. And so charges are going to be less than +4 or -4 because we only have 8 electrons to worry with. Okay? And the periodic table helps us predict charges. So let's take a look at that. The charges here, let me move my little window down to things we don't care about as much. Okay. So the periodic table helps us predict charges. Remember that if something has 1 or 2 electrons, it's going to be over here. And then if the outermost energy level is the P's, then the outermost energy level has 3, 4, 5, 6, 7, or 8 electrons in the outermost level. And for the most part, ions are going to be formed so that something can have a full energy level in its valence shell, so that the outermost shell of electrons is full. So if something is almost full, it would like to pick up a couple more electrons to be full, which means it's going to become a negative ion. So if something is in this column, it has 7 electrons in its outermost energy level. It wants to have 8. It wants to be like a noble gas. And so it would like to pick up just 1 more electron. And then it'll be happy. It'll have a full energy level on the outermost shell. So that means that all of these will become -1 ions. Fluorine, chlorine, bromine, iodine, astatine, and these guys will always become -1 ions, because it only takes 1 more electron to fill up its shell. Similarly, these guys over here, they only have 1 electron in their outermost shell. If they dump that one, the shell underneath is full. So they would like to get rid of the one lonely, sad electron that they have in their energy level, in their outermost energy level. And they will always become positive 1 ions, because when they lose an electron, they have 1 fewer electron than protons. So they will always become positive 1 charges. So on the edges of the table, it's really clear. These will always become positive 1. These will always become positive 2. These will always become negative 1. These will always become negative 2. But now as you get into the middle, these guys, they're 3 away, or they have 3. These guys have 4. And so these guys could actually become positive or negative 4. These guys could become negative 3, and occasionally in strange situations you see positive 5 ions. These guys could become positive 3, or in some strange situations, negative 5. So the ones in the middle are a little bit harder to work with. They're not quite as clear. But certainly the 2 columns all the way over here are always negative 1, always negative 2, almost always negative 3. These are positive 1, positive 2, almost always positive 3. The one in the middle, it can go either way, okay? And so the periodic table helps you predict ionic charges. Transition metals are confusing. Don't worry about it. These guys are even weirder. Don't worry about it. Most of our chemistry is going to deal with the S and P blocks anyway, and so just be familiar with those, okay? And that helps you understand why the noble gases, and we'll get to them in a little while, why the noble gases almost never form an ion, because they have a full energy level. Why would they give or take? They're happy the way they are, okay? So there's that. Okay, so that's ions. Ions are the changes in the number of electrons versus protons. Now, we may also change the number of neutrons. Neutrons don't control what the identity of the atom is either. So something with 6 protons, always carbon. Doesn't matter how many neutrons it has, it's always carbon if it has 6 protons. When we change the number of neutrons, we don't change the charge, because neutrons don't have charge. They're neutral, hence their name. But we do change the atomic mass. So carbon normally has the mass of 12, and that's because it has 6 protons and 6 neutrons, and 6 and 6 is 12. But if we have more or less neutrons in that particular atom, it's still carbon, but it's no longer carbon 12. It is carbon something else. And we call atoms that have a different number of neutrons an isotope, okay? Isotope, iso means similar to or mirror image, and I don't know where tope comes from, but we're talking about a similar atom to the other kind, but it's different in the number of neutrons, okay? Same chemical properties, but they may be different in radioactivity. Carbon-12 and carbon-14 behave exactly like each other in chemistry. You are made up of a mixture of carbon-12 and carbon-14, and the parts of you that are made up of carbon-14 behave chemically exactly like the parts of you that are made out of carbon-12. No difference in chemistry. The difference is that the parts of you that are made up of carbon-14 are slightly radioactive. Congratulations. When you change isotopes, you don't change chemistry, you sometimes change physics. The radioactivity of it will be different, okay? So the example here for carbon-14, 6 protons and 8 neutrons makes carbon-14, which is very, very, very slightly radioactive. Where's my mouse? There it is. So here's the different carbon isotopes, okay? Carbon-12 is the normal carbon. Almost all the carbon in the universe is carbon-12, 6 protons, 6 neutrons. There is a very small part of the universe that is made out of carbon-13. It's even less than the parts of the universe that are made out of carbon-14, and they're minuscule slivers, right? But part of it is. And carbon-14 is radioactive. Carbon-12 and 13 are stable. Carbon-14 is radioactive. And the difference is just the number of neutrons. This has 8 neutrons, this has 7 neutrons, this has 6 neutrons. But they all have 6 protons, and they would all have 6 electrons in a neutral state. Okay? So ions change charge, neutrons are different isotopes, and just change radioactivity is the only thing that makes it different. Okay? We talk about an isotope and its weight. And so when I was already using this term, and nobody was confused with like understood what I meant when I said carbon 12, carbon 13, carbon 14, right? It's just the weight of the element. So we denote the kind of isotope that it is by putting the elemental symbol and its weight right after it. Carbon 12 is the normal carbon. Carbon 13 is a very small fraction and is also stable. Carbon 14, slightly bigger fraction, but still very small and is radioactive. So you may have heard of like uranium-231, and that is the radioactive uranium that can be used in power plants and nuclear devices and things of that nature. There are other uraniums that are not radioactive and are stable. So different isotopes will be distinguished by giving the elemental symbol and its weight. When its atomic weight is written on the periodic table, it's an averaged weight, taking the average of all possible isotopes in their proportions. And you're going to do a lab with this tomorrow. So if you look at the periodic table, and I think I have a slide of it next, but when you look at a periodic table, the masses are not whole numbers. So we said carbon 12, carbon 13, carbon 14. But if you look at the periodic table, the mass for carbon is given as 12.011. And you're like, wait a minute, how do you have 0.011 things in the nucleus? You don't. Carbon is either 12, 13, or 14, but it's almost all 12. There's just a little bit of 13 and a little bit of 14 out there in the universe. So when they represent that, they list the weight as 12.011 to represent the fact that it's almost all 12, but there is a little bit of stuff out there that's heavier. And so they average all of the known isotopes for an element and the proportions of those isotopes in the number that they put on the periodic table. So when you look at masses and you see numbers that are decimals, don't get confused and don't think that carbon has 6 protons and 6.011 neutrons. That's impossible. But it's just that almost all the carbons have 6 and 6. Some have 6 and 7, some have 6 and 8. And so when you average all of that together with the proportions of what's out there in the world, the answer is 12.011. Okay? So it's averaged weights on the periodic table. And there you go, I showed you that. Almost all the carbon has a mass of 12. Since a small number of them have masses of 13 or 14, the mass is averaged to 12.01. That's what it is in your textbook. On the periodic table up here, it goes one more decimal place, 12.011. Okay, do you guys understand that idea? Cool. So, how do you find the average atomic mass of something? You take the percent of the sample that is a certain weight, and you multiply it by the weight, and you add that weighted average up, and you get an answer. So in the case of carbon that we've been using this whole lecture, you know, it's 99.9% carbon 12. But there is a very small percentage that you would multiply by 13, and a very small percentage that you would multiply by 14, and then you add them up, and you get 12.011. Okay? So that's how you get a weighted atomic mass, or a weighted average. Give me a second to finish writing it down. It didn't take as long to talk about it as it does to. So this is an example of calculating an atomic mass. Now we're looking at magnesium. Okay, magnesium has the atomic number of 12 and the atomic mass of 24.31. So the atomic number is 12, which tells you it has 12 protons. The atomic mass is 24.31, which tells you that most of the time magnesium also has 12 neutrons. Because if you were to round that to the nearest whole number, the answer is 24. There are 24 things in the nucleus, 12 of them are protons, because that's the atomic number. So most of the time, magnesium also has 12 neutrons. But the number is a little bit bigger than that, 24.31, telling you that sometimes there's more things than that in the nucleus, right? So here's how you would calculate the atomic mass. In all of our samples, now obviously we can't go out and sample everything in the universe, but in all the samples that we have gathered of magnesium out there, 78.99% of the time it's magnesium 24, okay? And so if you take 24 times 78.999, you get this number, okay? 10% of the time it's magnesium 25. So 25 times 10, and I don't understand, actually, I'll be honest with you, I don't understand why this isn't 25. I don't get that, but okay, let's just say it's 25. 25 is approximately 2.5, okay? You have this number. Magnesium 26 is 11.01% of the time. So 11.01% times 26 gives you this number. You add those numbers up and you get 24.305, lots of change. You round to the number of significant digits that you had in your abundance, right? 4 significant digits. So you need to have 4 significant digits in your answer, 24.31. That's how we get 24.31 as the average atomic mass. Does that make sense? Okay, so that's how you get average atomic mass for things. I think that's the end of my slides. Yes, it is. What questions do you guys have?